Ignition sequence start. All engines are running.
We have taken tremendous steps.
We choose to go to the moon before this decade is out.
We have achieved the earth-shaking, the breathtaking, the groundbreaking,
One small step for man.
and left a mark in the heavens. Our successes build one upon another and amplify what is possible.
The dawn of Orion.
It's time we take the next great leap. We're building the next chapter of American exploration, returning to the moon to stay, so we can go beyond to Mars, to expand what's possible and further our understanding. The architecture for these missions is already taking shape. We will go with new systems, bold designs, and a sustainable mission. You can hear it, taste it, touch it. We are going. We are training, testing, pressing our pioneering spirit into every component, defining our resolve with every line of code, and securing our success with every welcomed partnership. This is not hypothetical. This is not about flags and footprints. This is about sustainable science and feeding forward the advance of the human spirit. Because we are the pioneers, the star sailors, the thinkers, the visionaries, the doers. And because we stand on the shoulders of giants to go farther than humanity has ever been, we will add our names to the rolls of the greatest adventurers in history. Every day, every mission, we advance this calling. We are NASA. And after 60 years, we're just getting started.
Hello and welcome to the live virtual connection event for NASA's App Development Challenge. Today's event is the second in a series of 3 live virtual events where we provide information, resources, and best practices for those participating in the App Development Challenge. My name is Jamie Semple, and I'm a NASA Education Specialist with Paragon Tech. I work at NASA's Johnson Space Center in Houston, Texas, and I'll be providing all the information on the challenge today. We are joined by 2 NASA subject matter experts who will provide 3 presentations on essential aspects of the challenge and best practices for creating an app. They will talk a little bit about creating a visualization utilizing the Lunar data file and 2 additional presentations on game engine use. The App Development Challenge is a coding challenge where NASA presents technical problems to middle school and high school students seeking student contributions for future exploration missions. This year's App Development Challenge was created in collaboration with NASA's Space Communication and Navigation team, also known as NASA SCAN. The NASA SCAN needs a visualization of the moon's surface. Based on this need, we are asking students to form teams and create a visualization of the moon's South Pole region. Teams will utilize provided lunar data to create a visualization that shows essential details for communication and navigation. Teams then will submit a video of their app solution online for consideration by NASA in future exploration missions. The challenge started on September 30th and concludes on November 18th. However, if you're just joining us today for the first time, there's still plenty of time to register as registration closes on October 28th. Throughout the presentation today, we encourage you to go ahead and post questions in the chat, and we'll try to answer those along the way, and we'll definitely have some time at the end of the presentation to answer any questions that you have. So let's go ahead and get started and take a look at our agenda for today. So we're going to start off by talking a little bit about the NextGen STEM project, and then we'll do an overview of the App Development Challenge, and then we're going to have those 3 presentations provided by our NASA subject matter experts. At the end, we'll answer some questions, and then we're also going to provide you some information on new NASA opportunities that you can take part of as joining the Artemis generation. So let's take a look at NextGen STEM. This is a project that is based out of NASA's Office of STEM Engagement, and it provides a lot of different opportunities and resources for students to directly contribute to the work that NASA does. Within NextGen STEM, there are 4 mission-driven focus areas. Those are Commercial Crew Program, Aeronautics, STEM on Station, and Moon to Mars. The App Development Challenge is part of the Moon to Mars project, and Moon to Mars provides information on NASA's exploration campaign for returning to the moon and going on to Mars, specifically with the Artemis program and Mars exploration efforts. Moon to Mars provides a lot of different opportunities and resources, including videos, webinars, educator guides, and student challenges, just like the ADC. There are 5 Moon to Mars student challenges. In addition to our challenge, we also have the Rover Challenge, WARE Challenge, Student Launch, and Roads. So a lot of different opportunities. If you're interested in additional challenges, you can go to those websites and check out that information. So let's go ahead and talk a little bit more of the App Development Challenge. Like I mentioned, you're going to create a visualization of the Moon's South Pole region. Based off of our collaboration with SCAN, SCAN can utilize this for future mission planning and training activities. And what you're going to do as part of that visualization is identify an exploration path and identify 10 communication checkpoints. So the main purpose of your app is to keep astronauts in constant communication with a satellite or a ground-based Earth station, and obviously plot a path for exploration that keeps them safe. So we'll talk a little bit more about that in just a moment, but let's take a look at who is eligible for the challenge. So it's open to any informal or formal U.S. education organization. So that includes schools, science centers, after-school programs, scouting groups or organizations, and as well as U.S. schools at military bases around the globe. Teams must be either a middle school or a high school team, and students can only participate on one team. All teams must be led by a lead teacher who is a certified and practicing K-12 educator. And finally, you must have a signed letter of support that is submitted at the time where you send us an email with your intent to participate. That signed letter of support must come from your principal or administrator. These are a couple of the key eligibility requirements. But you really want to go to the ADC website to find out all the eligibility requirements or reference the ADC guide. So we'll talk a little bit more about the ADC guide in just a second. Let's go ahead and go on to the next slide. All right, so like we mentioned, you're going to be creating an app that will visualize the Moon's South Pole region. You'll have 7 weeks to do that. We're actually 2 weeks into the challenge, so there's 5 weeks remaining. And at the conclusion of that, on November 18th, you'll actually submit a video of your app solution. So you're not actually going to send us your app, but you're going to send us a video. It's a 5 to 7 minute video, and it's going to outline exactly what we had asked for as far as requirements in the ADC guide. So there's a script that's provided, and you'll go ahead and answer the questions in the script, and then film that, and then you'll submit that video in an unlisted setting on YouTube for us to review. At that point in time, we'll take a few weeks to review the videos, and then we will down select to a smaller group where we'll actually ask you to participate in interviews with the ADC and SCAN teams. Eventually after that, we will spend some time down selecting again, and then we will select teams for a culminating event experience. So like I said, we are 2 weeks into the challenge. If you didn't get an opportunity to join us for the live virtual kickoff event on September 30th, we encourage you to go ahead and go back and watch that video. We can go and place that in the chat so you have that link, but that goes into detail on all aspects of the challenge. And it will really give you some good detail on the technical aspects as well, because we asked our ADC technical advisor to join us to go over the data file and some best practices for developing an app. So let's go ahead and take a look at the ADC guide and the coding components. Once again, they're available on the ADC website now. I encourage you to go there. If you haven't downloaded the guide so far, go ahead and do that. Read that cover to cover, and I'll have all the details that you need to be successful in the challenge. Once again, eligibility requirements, there's a longer list than the one that I just talked about, and there's some detailed information on how to create your app. So that goes hand in hand with the lunar data file, which I'll talk about in just a moment. But you definitely want to be aware of exactly what we're expecting in the app that you're going to create. As far as how you'll be scored, we have 2 scoring rubrics, one for middle school and one for high school, that directly aligns with the script that I just mentioned. And you just look at those details and start to figure out a way that you're going to design and then create your app. So there's a lot of detailed information for the scoring, so make sure that you're definitely looking at that, because there's a big difference between middle school and high school. Also, the timeline is in there, and we'll take a look at that in just a moment. But the next is the lunar data file. So this is all the data that we need you to visualize in your app. And once again, if you go to the kickoff event on September 30th, you'll hear a lot more from our technical advisor about that data file. But effectively, that has latitude, longitude, slope, and height. And we need you to utilize that to create the visualization, and of course, plot a safe path for astronaut exploration, and then identify places that you can communicate back to Earth. So keeping our astronauts in constant communication with Earth, and at the same time safe as they traverse the surface of the moon. Next up is a terrain texture, which is actually a PNG file. You can utilize that to create your visualization. You don't have to use that. You can use a different texture. You can create your own. You can use anything that's online. But that will definitely get you started if you'd like to go ahead and use that. So let's talk about the route information, specifically how it is constrained by way of slope. Let's go to the next slide. So within the data file, it's going to tell you exactly where your landing site is and your destination site or exploration site. And here you see the slope data actually displayed by way of color. So anything that is yellow is safe. Anything that is blue is not safe. That's based off of a requirement of keeping it minus 15 degrees of slope or less. So you'll plot that path for exploration. There's a couple different ways of doing that. And of course, there's a couple different ways of displaying this data. Your goal is to take the data we provided and visualize it in some useful form. So if it's a point and click with the actual data set, if it's by color, whatever way you would like to do that, you can go ahead and create your app that way. We don't restrict anything when it comes to the language or how you would like to create this visualization. However, the scoring rubrics will help you understand what we're looking for in the overall app. So you definitely want to check that out. So then we'll take another look at the 2D terrain data. And you'll see in these two pictures just the height and slope displayed. So that in this case, we visualized it with color. And then let's go and take a look at the 3D picture. Ideally, we would like an app that shows the lunar surface from the perspective of the astronaut. That is not required, and it's a different scoring between middle school and high school. But you'll see what type of points you would get depending on how you develop your app. For high school, it's actually mandatory for the maximum points. In some cases, it's required for a specific section in that scoring rubric. So let's take a look at the timeline and talk a little bit about what's going to happen in the next 5 weeks. Of course, we have our live virtual kickoff event on September 30th. We encourage you to watch that as soon as you can, maybe after this event. And then, of course, today's live virtual connection. The next one up, the final one that is available to everyone, which is the third event, will be moving, like I mentioned earlier, most likely between November 2nd and 4th, and we might even change the time, and we'll provide that information as soon as possible. And then the 28th is also the last day to register. So if you haven't registered, you're in the process, go ahead and wrap that up before the 28th. If you know of anyone else that's interested, please share the information with them. But at that point in time, we will close our registration, and then we'll have our final live virtual connection. That's just for registered teams. So you can join us for one more event before it's just the teams that will be participating all the way to the video submission deadline. That deadline is November 18th. All videos must be received by 2 p.m. Central Time, and they must be posted on YouTube in the unlisted setting. And once again, all this information is in the ADC guide. It'll take us a few weeks to do our review process, and then we will select teams for interviews, and then based off of the interviews, we will select some teams for a culminating event experience. And right now, we are targeting February 16th to the 18th for that. And we can go to the next slide. Ideally, we would actually have that at NASA Field Center, but right now we are making plans to switch to a virtual student symposium. It'd still be the same dates, but we're just being mindful of the current conditions in regards to the pandemic, and we might have to adjust to that virtual event. So more details to come. We will obviously let you know as soon as we finalize any change of plans. But we definitely want to take a moment, in this case, a couple days, to acknowledge all your hard work and give you the opportunity to present to NASA what you have created. So a real quick overview of the ADC. We really want to get to our presentations today. But if you have any questions, I can go ahead and field a couple of those questions. Let me see if there's any available. And if not, we're going to go ahead and go on to our subject matter expert presentations. All right, when are the projects due? They're due 2 p.m. Central Time on November 18th. And there's a great question in here about utilizing Python and the Unreal Game Engine. So I'm going to go ahead and wait on that until we get to Tanner's presentation. And I'll go ahead and introduce our guest today. So I'd like to introduce Jonathan Schlueter and Tanner Hunt. And they are software and simulation engineers with CACI International. And they work as part of the team with part of the JSC Virtual Reality Training Lab team here at Houston, Texas. So they're going to tell you a little bit about how to take the lunar data file and create a visualization, and then 2 additional presentations, like I mentioned, on Unreal and Unity. Just a little bit of information on the JSC Virtual Reality Training Lab. It's been in operation since the early 1990s, developing tools and software for astronaut training and extravehicular activity, which is also known as a spacewalk. So they're going to go ahead and tell you a little bit about the 3 presentations that they have created. And with that, I'll go ahead and turn it over to John and Tanner.
Thanks, Jamie. Howdy, my name is Tanner Hunt. I was born and raised in Denton, Texas, just north of Dallas. I got my bachelor's and master's degrees from Texas A&M University, studying aerospace engineering. During that time, I worked 3 internships at NASA Johnson Space Center and 1 internship during grad school at Lockheed Martin in Colorado in their virtual reality lab. I started at CACI this past January and have in total a little over 3 years of VR development experience. In my free astronomy and astrophotography, on the bottom left and the bottom right is some of my work. The bottom left is actually a picture of the International Space Station, and the right is a picture of Saturn I took from my backyard. So I thought that was pretty cool. And besides that, I enjoy hiking and video games. So yeah, with that, I'll go ahead and pass it to my colleague, Jonathan.
Hi, so I'm Jonathan Schleter. I am born and raised in Iowa, and I went to Iowa State University, where I got my undergraduate in computer engineering, and I got my master's in computer engineering and human-computer interaction a couple years later. And so I got my start in virtual reality about 7 years or so ago when I started working at Iowa State's Virtual Reality Applications Center, which kind of exposed me to what simulation and virtual reality and virtual worlds can do for all sorts of different industries. And so from that, it gave me an interest of what I can do. And of course, space is very exciting. And so I decided I wanted to apply that down here. And so I started at CACI's JSC VR lab back in mid-2018. And I've been since there ever since. So some of my hobbies when I'm away from the computer are I love the outdoors, so I go camping and hiking when I can. I love playing music, so either guitar or piano, and I do enjoy my fair share of video games too. So without further ado, we can jump right into some of the ways you guys can get started with this challenge. So first up, you need to figure out a way to get your data into a visual format of some sort. And so one option to do that, that's one of the more straightforward ways, is you create a mesh from it. So you use the latitude and longitude and the height from this data file, and you convert that into an X, Y, and a Z in 3D space. And each of those X, Y, Z vertices you use as a point in your 3D mesh. And so a benefit to this is it's a true to life representation. You don't have to guess about where things are. It's exactly where it needs to be. The problem with this is it's very hard to adjust. Once the model's been created, you have to manually go in there and move each of those points. So the way you can go about doing this is, there's numerous ways. I'll show you one. You can create a plane with many vertices in it, and it's all just flat. And then you read in this CSV file, and for each line is the data point, and then you set the corresponding XY position with that model vertex to the given height. And you'll end up with something in the bottom right picture there, where if you zoom in, each of those individual points is an individual point in your data file. Now, obviously, you're going to have to make sure your data is spaced out, so your plane isn't 5 meters long versus the several kilometers of your data file. And you're also going to have to think about smoothing and other ways you're going to be able to visualize that a little more. Now, a second way you can look at doing is what's called a height map or a displacement map. And what this does is it essentially creates an image for whatever area you're looking at that tells a system or computer what height that terrain is at. And so it's a grayscale image, it's black and white, and it represents a terrain. So what you do is you take this image and you apply it to a plane. And just like in the previous one, you just moved each point. This one, it uses algorithms inside of software that you don't have to write in order to get all those offsets for you. So a benefit to this is you can easily resample it, so you can change the visuals without a whole lot of manual work. And most renderers support height maps, whether it be Unreal, Unity, multiple other ones, even a lot of modeling programs, like I'll show you here in a few minutes, are able to handle that data really well. An issue with this that you want to keep in mind is it can desynchronize the data between the exact coordinates that are in your file and what's on your mesh. Since you're working from an image now, images are pixels, and pixels have nothing to do with the model itself. So you'll have to keep that relationship in mind if you ever need to go backward from your 3D model into your data file. So the method to go about doing this is you take your latitude and longitude and you determine what pixel this is going to represent from left to right, top to bottom. And then what you do is you read the height value, and you want to rescale your height values so that the lowest height you see in the entire file is going to be pure black. So it's the lowest point in your file, and the tallest peak of the lunar terrain that you're looking at is going to be pure white. So if you look in the image in the middle there, the white areas are much taller and the dark areas are much lower. And so whenever you apply that to a plane, you'll get that three-dimensional model that you have. So an example, in a 16-bit grayscale image, the lowest value will have a value of black or 0, and the tallest will be an integer value of 65,535 as pure white. And so some of the tools that you can use in order to work with this data, one of the ones that's primarily used for many people that is free is called Blender. And it's a modeling software suite that has all sorts of different tools as well as a Python scripting environment in the back end. So you can actually take this data and read the CSV in and apply it using Blender's own functions and Blender's own capabilities. And so you can actually use that to create that mesh like we were talking about in method 1. You can also use, if you've generated it from a different program, a height map inside of here. And instead of creating a mesh, you could use what we were saying with method 2 and apply a height map or a texture, grayscale texture, and displace a plane in order so it shows up something like you can see off to the right there. And if you remember, when it gets really jagged, there's going to be ways you're going to need to smooth the data and figure out better ways to visualize it if you're actually sitting on the surface. And so Blender and a lot of other modeling tools apply modifiers, and you can change the look of things so you can smooth over the edges, and you can do a lot of things with that. One thing you'll need to keep in caution is as you're smoothing, you want to make sure how you are doing it, or you will actually kind of shave off the peaks and the valleys, and your height data won't be near as accurate as it was before it was smoothed. And so this is only one option. There's a couple links down there of other projects that essentially turn a height map into a 3D model that you can work with. And those are just a couple examples. There are numerous ones you can find online if you find something works better for you, or if you wanted to actually create your own solution. And so with that, we can actually go into a project we have been working here at the Johnson Space Center of actually doing a very similar job of recreating the lunar South Pole terrain near the Shackleton crater. So we've got a video we can show you guys. So this is a multiplayer environment. So right now we've got 2 people in the same scene. And in front of you there is the Shackleton crater. It's about 20 kilometers wide and several kilometers deep, bigger than the Grand Canyon. And one of the players is driving around a rover around the simulated terrain there. And the data we're seeing right here is actually taken in 10-meter increments as opposed to 40. So it's a little higher fidelity as opposed to what you're walking on. And you can also see the rock field there as well. And so that's a random scattering of 13 different samples that we have that were X-rayed from the Apollo era, and they were digitized into a 3D asset that we then took and put inside of our simulation here. And then we took those rocks and scattered them around, so then these crew members can actually use real samples brought back to learn what's useful and what's scientifically interesting to look at for samples whenever they're back there taking samples, hopefully in just a few short years. We also add a bunch of interactive capabilities to this to add to the immersion. So as you saw, that crew member was able to walk up that ladder using his hands to kind of pull himself, since the virtual world doesn't usually have a physical ladder there sitting next to you. And what just happened is the sun dropped below the horizon. So before it was the lunar summertime, and now it's the lunar winter time. And that is about as far as the sun's going to move. It's never going to be up in the sky at the south pole of the moon, just because it's tidal locked with the Earth. And so what that does is it will have very long shadows. And that's one of the most interesting things about the South Pole, is that it has permanently shaded regions in the same close proximity to permanently lit regions. You need permanent sunlight in order to power solar panels, in order to keep batteries powered and everything like that. But you also would really desire permanently shaded regions, because that is where a lot of the interesting stuff happens. The lunar ice, a lot of the samples that have been non-bleached by the sun, and a lot of those kind of things. And so we built this environment as a base level in order to fit into all sorts of different simulations, whether it be soil sample gathering or communication, so we can all understand how that's going to look on the South Pole. And so going to the next slide, this was actually made in the Unity game engine. And so what this is it's a game engine, and what that means is it integrates a bunch of capabilities together. So it can do your rendering, your visuals, it can integrate physics, like you were showing, we were throwing rocks around. You can also have a scripting environment in order to customize how objects in the scene behave and how you're able to read in data files. It can also have a lot of different assets like path planning or terrain editors, which we'll go over here in a minute. And it takes all these assets and puts them together in a single space, so you don't have to manually do all these different pieces in different platforms and try and integrate them together. And so one thing we can take a look at is, what does Unity scripting, and how are you going to be able to read a file into Unity? And so it's based on C# is the programming language. And what's available to you whenever you create a script inside of Unity by default is Unity's libraries, which allow you to interact with the visual elements and the back-end physics of Unity, as well as Microsoft's .NET libraries. So anything with those you are able to use in a Unity script that you can apply to your video game or your simulation. And so once you get this file in and you read it, you're able to use that latitude, longitude, height, and slope and all that data to actually interact with this Unity engine. So one thing I had done was I took the file and I read in the points, and then I did a little conversion to get the latitude, longitude into a circular format of this 88 degrees. And every 100 or so points, I made a little sphere. So the little image there is essentially a very basic reproduction of what it would look like if we took that data file and randomly sampled a few points and put a little sphere on them. So you can kind of see the Shackleton crater in the middle of that image, and you can kind of go out from there. This would not be of any use for you guys to create your own terrain, because it would be extremely slow and laggy, and not even good computers would be able to run it, because there's several 100,000 spheres. That's not how we want to visualize data. So that's why it's better to go through the process of actually 3D modeling and connecting all of those joints to a single model rather than a visual like that. So a way you can go about creating and bringing in this data, first you need to load this CSV file into Unity. You just drag and drop it in the project assets. And then you go to create a script, and then you can read in this data file. The first thing you need to do is create a way to store the data that you're reading in from this file. Whether you want to create a custom class object that has 4 values for your latitude, longitude, height, and slope, or whether you want to just have multiple lists of float values, or however you want to handle it. Once you get that created, then you can load in the file. And there's numerous ways to do that. And Unity is a very well-used, well-documented game engine. And so there are a lot of different tools available for you. So you can either use Unity's text asset, you can use C# Stream Reader. There's even a CSV reader if you wanted to be more direct with the approach. So you can look at all sorts of different ways in order to get that data read in. So once you read it, you can read each line in a loop, and each of these lines is separated by a hidden new line character. And that's what tells the little text editor, okay, we're going to go to the new line. What's the next line? And so each line is then separated by commas. So you can take a look at that and use your parser to get this data and read it in. And one gotcha is to make sure you convert the string value that you read in for this number into a numerical representation. Because whenever you read it in using a string, it is still in a string value. A number 1 can still be the character number 1, and the computer's not going to understand that as a number rather than just a symbol. And so once you get that converted, you can then do all sorts of things like have fun and print out little spheres at every little vertice that you want around the terrain, just so you can quickly visualize it to see if it's inside of Unity and you're able to use it. and then all sorts of different things. You can also go the reverse and say, I've clicked on the terrain. At what point did I click? And you go back to see what data point and what the actual height that you've read in is. And so Unity also provides a few tools specifically that you would be of good benefit to you. So it has a terrain editing tool, which takes a height map, which we've been talking about, and it takes a texture, and it combines those two together to create a terrain. So if you go this route, you don't actually have to create your own 3D model as long as you have a height map there to be used. So you can use this in custom landscapes. You can import and convert these height maps into this 3D geometry, which works directly inside of the Unity game engine. And then you can use a material editing workflow to then change the coloring of it, change if there's rocks there, change if there's soil. Lunar is a very relatively similar terrain, so you won't have quite as much diversity as you will on Earth. And one of the links there on the bottom that we'll send out for you guys actually takes these two images and guides you through how you're able to create that mountainous terrain on the top there. So your guys' job would be able to, if you wanted to go this route, is to figure out how to create that grayscale height map in order to plug into Unity and use their engine. Now, another tool that you guys might find useful is their navigation and pathfinding capabilities. So just like they have a terrain editor, they also have a navigation editor. And you can see that kind of in the work there on the right-hand picture. Is what it does is it uses tunable parameters. So you have a max slope or a step height, like you're walking upstairs. And then it analyzes your 3D model that you integrated, that you asked it to look at, and it will paint and say, based on what you've told me I can walk on, where on this 3D mesh can I walk? And the blue parts there are what you can you are capable of walking around. And then it has a navigation component to that once you've baked in this pathfinding of going from point A to point B. Now, this works very well in a little tiny box like that. You might have challenges whenever you try and use it at the several kilometer scale range that you're going to see in this lunar terrain that you're going to recreate. So this is another tool available for you to take a look at and see what you can get out of it, and gives you some capabilities. So that kind of wraps up some of the data that we've kind of looked at and some of the tools you can use, as well as a basic overview of some of the Unity game engine application systems you can use.
All right, thanks, John. We do have a couple questions for you, and I think that you've actually answered some of them in the course of your presentation, but let's go ahead and see about answering a few of those. Let's see. You talked about the video that you showed. Was this done in Blender? You said that was done in Unreal. So, excuse me, Unity. Was the entire thing done in Unity?
So the terrain itself was actually done in Blender. We took a height map, like I showed you several times, and in Blender we created a 3D static mesh. And then we brought that into Unity and we tiled it up. So we actually have 160 kilometers by 160 kilometers in a square. And as you get closer and closer to different edges, you can then transition to a different block without having to show the highest amount of detail all the way out to the horizon. So we actually have 3 levels of detail that they can see. One that you're standing on, which is the 10 meters per pixel, the far distance, which is 40 meters per pixel, and then the far terrain, which is 160 meters per pixel, which is more than enough to say, if the sun's going to go behind this, then it will obscure the sun and cast a shadow on our current location. But all of the scripting, the visual elements, as far as the shading and everything, that is all done inside of the Unity game engine. The only thing that was not was the 3D modeling of the surface itself.
Okay, so we had a couple questions about reading in the lunar data file. How do we do that? And then a second question about it would not fully load when they tried to download it. There is over 7 million lines of data. So what are you recommending as far as with the Unity platform and making sure that that data gets in there correctly?
Right. So it treats it as just any other asset. So whenever you have the Unity editor open, you should be able to drag it in. It's a 70 megabyte file, I believe it is. And you can drop that in. And then a couple ways to read it is in your script, you can define a public text asset. and then you can drag and drop from your assets folder into that script public variable, and then you'll be able to interact with it that way. That's how I was able to read in the data and recognize where that data is in that little picture I showed you from that. That has worked. There are other ways to do it that is less direct, but that has been the most simple for me. And let me know if you do have issues with that, or if there's an error that's coming up or something like that. I can give a little assistance. But
Okay, a couple other questions, and I'll answer a couple of these. Are we required to create a 3D app, or could a 8-bit or even just a 2D app work? It's really up to you. Depends on the composition of your team, the resources available, and how you would like to create the app. Once again, I encourage you to look at the scoring rubrics to see kind of where you will fall as part of that process, and whether you're a middle school or high school team. Obviously it's going to be, the 3D aspect of it is, like I mentioned, is required in certain parts of the high school scoring rubric, but it's really up to you. We really want to see what you're able to create with this. I'll just take a moment to say that not all teams are going to 100% complete the development of their app. That doesn't mean we don't want to see what you were able to do. We really want you to work through the process as a team to try to create this visualization in the app for Scan to use. But if you don't get it all the way to the end and complete it, we still want to see what you were able to do. So those are just some of the aspects that you encounter working on a short timeline and with the team. So once you decide some of those specifics, if you get down the path and you're not too sure if you're going to be able to complete that work, like I said, we still want to see what you're able to create as part of your team. All right, does the Unity pathfinding tool work with both the mesh and height map approach, or only the mesh?
So from what I've used, I've only used it on the mesh itself. So you tell it what mesh to use, and then it analyzes the geometry of it down to the vertex level and says, what is the slope of this model? And so it doesn't use the height map directly that I know of. You might be able to find a way around it, but it primarily looks at the 3D mesh and the geometry of it, and then takes your slope input and takes those kind of things and says, what should I be able to walk on? And going back to your last question, Jamie, both Unity and Unreal and several other tools are extremely useful in 2D as well. If you don't even want to use anything with 3 dimensions, it has an entire mode of the engine you can toggle into a 2-dimensional space.
So that's great. So if teams are trying to consider which way to go, they could utilize either option. A couple questions about if this is being recorded and will the slides be available. As soon as we are done with this event, it will be available at this link location. It's available on the NASA STEM YouTube, so you can watch it as soon as we are done. Let's see what else we have. Can we use any architectural or engineering software like Revit or Maya?
Absolutely. So Blender was just one tool that we showed to you guys because it's free and open source. If Maya works for you guys, absolutely use it. And Revit I've not used myself, but I've heard good things too. So if you find resources and a way to go about it, then absolutely try.
All right, so there's a lot of other questions. We'll try to answer these at the end because it kind of summarizes today's presentations. At this point in time, we're going to go ahead and turn things over to Tanner. He's going to talk a little bit about taking the ADC Lunar file, and if you're utilizing Unreal, what are some of the best practices and resources available so that you can be successful. So Tanner, go ahead and take it away.
All right. Excuse me. Thanks, Jamie. So at a high level, Unreal Engine 4 is very, very similar to Unity. I personally started out using Unreal Engine 4 back when I first started doing 3D visualization and VR development. And in my opinion, once you learn one, the other is very easy to pick up. So either way you go, can't go wrong. And again, these are only 2 options that we're presenting. There are other options out there. So like I said, at a high level, 2D or 3D scenes can be constructed in the editor in a very similar manner to Unity. There will be cosmetic differences between the two, but for the most part, the tool set and the methods used in both are essentially the same. There are definitely some notable differences, including the following. So like Jonathan mentioned, Unity uses the C# programming language for scripting, while Unreal Engine uses C++. The learning curve for C++ may be a bit steeper, However, Unreal comes with a great tool called Blueprints that enable what's known as visual scripting. So basically, instead of writing lines of code, you can add predefined function blocks to this graph interface and connect these blocks with wires to add your functionality. So it's a great way to quickly prototype your logic without having to write a single line of code. An example of a blueprint can be seen here on the right. Oh, sorry, back one slide. And so as you can see, this logic is very straightforward. You're just connecting these boxes with wires. There's no code involved. I really enjoy this method. It makes things very easy. But for quick prototyping, it's great. But as we can see here on the next slide, things can get very complicated very quickly. This is what we like to call spaghetti code. So, and this is a very organized example of spaghetti code. But so in a case like this, it may end up actually being simpler to code in C++. And that really just all depends on the situation and the functionality you're trying to achieve. So, just as a kind of reference here, this blueprint graph that you see on this slide, it's pretty complicated. That probably took a good amount of time. Whereas in C++, you may be able to do this in 100 lines of code. So you have to weigh your options and kind of determine what's going to be best for your situation. So as far as the terrain tool goes in Unreal Engine, it offers a great terrain tool out of the box. It's very powerful, comes with a lot of cool features, and it takes a grayscale height map, just like the one in Unity that Jonathan talked about, as an input and produces a 3D mesh. And you can see that here in the example on the right of the Apollo 17 landing site, and works the same exact way. So your dark spots are going to be the lower regions and the bright spots are going to be the higher regions. So some of the key features that Unreal Engine's terrain tool includes is a sculpting tool that allows you to edit landscapes or create your own from scratch. That's not particularly useful in this challenge, but it's good to know that that tool exists. And also, just like the modifiers in Blender that Jonathan mentioned, this tool can alter the landscape by smoothing things out, changing elevations, adding foliage, or in this case, lunar rock samples and things like that. It also has a great terrain material editing workflow. So let's say you want your flat areas to be a slightly different material than your sloped regions. The material editor for this terrain tool will go ahead and apply those and blend them automatically. It's very, very easy to use, very powerful. Now, unfortunately, there is no way to, there's no built-in way to import a CSV into this terrain tool. We'll go over some different approaches to accomplish, how to get around that on the next slide. So given the data set for the ADC, as we've mentioned, there's no single best solution to accomplish this task. Like mentioned in the Unity section, your team can either convert the data to a grayscale image, which you can then use in Unreal's terrain tool, or you can use Python and Blender, just as an example, to create a 3D mesh that then once you have your 3D mesh can be imported just like any other 3D mesh into Unreal. As you probably know by now, that's only half the challenge. So on this next slide, we'll go over kind of these remaining requirements. So once your team has the terrain in Unreal, the work's not quite done. There are many ways to meet the remaining pathfinding requirements. So like Jonathan mentioned earlier, the data must be synchronized with the 3D mesh. And what that does is it'll allow you to pinpoint in your application the optimal locations along that path from the starting point to the end point. And some examples of ways to do this include the following. So again, you can parse a CSV file in C++. There's a lot of resources out there that will walk you through that process. Or you can use an Unreal data table, which is just it's just another way to kind of contain that data in Unreal and apply certain functionality to it. And once you have that, you can reference all that in your code or blueprints. And once the data is parsed, then you can use that as inputs into your pathfinding algorithms. Alternatively, the points can be calculated beforehand and then manually placed. So a great example of this can be seen in the downloadable demo of the Mars 2030 experience. It's available for free on the Epic Games Marketplace. And a screenshot of that is here on the right. Might be a little hard to see, but there are several paths leading to and from this Martian habitat that the in-game rover can then follow. So this project is a great example of just how powerful Unreal Engine 4 can be. And I highly recommend checking that out to kind of get an idea of all that functionality. So here on the next slide, I've got some resources related to the subjects that I just went over that you can use to get started. These will be posted in the chat for you to check out. And with that, I will pass it over to Jonathan to answer some of the key questions that y'all might have come up with after hearing our presentations.
So a couple of things you might want to keep in mind is, so the data sample you're reading in is taken at 40-meter increments. So every 40 meters, there's only going to be a single height for that latitude and longitude area. And so how are you going to be able to represent data whenever you're sitting close to the ground? So what a lot of people do is they use a synthetic texturing to lay whenever you're very close to the ground. It's kind of like how Google Maps works. Whenever you zoom in on the satellite view, the closer and closer you get to being at a human height, it blurs it out and it's very hard to distinguish what's what. And the same is going to happen for the lunar texture that you guys are going to receive, and a lot of the lunar textures you are going to find on the internet. And so what I would recommend doing if you want to get to that level of fidelity is finding what's called a seamless texture that you can layer one after the other, and it will blend together and create kind of this lunar terrain if you find a good seamless texture to represent that. Now, a second question, should the edges of the mesh be smooth since it was created in a grid or in pixels? And quick answer is it depends, again, on how detailed you want to be. There are a couple ways of smoothing the edges. One is to actually adjust the geometry in the mesh itself. So something called subdivision, it actually takes your mesh and then puts another vertice in between as two different vertexes. So it makes the mesh more dense, and so therefore it kind of averages and evens out some of those slopes. A concern with doing this is, like I had mentioned before, you could very easily cut off your slope, cut off your mountains, and cut off your valleys, and so that height data will then be a little bit inaccurate. Another way is to actually manipulate the lighting data and what's called the normals of your mesh. And so that is a cheaper way to do it, but it's a little more complicated in the way you have to write shaders for your camera and those kind of things. Now, another question is, does the curvature of the moon matter? And in the center of the South Pole, it's not going to, obviously, because that is the true to life representation. But as you go out toward that 88 degrees, what you guys started with would be a plane. But if you wanted to represent the curve of the moon, the edges are actually going to be a little bit more shallow and pulled in. And so there are a few different tools in Blender and otherwise to correct for the curvature of that. if you stay within a very short area, there's very low likelihood you're actually going to realize that you're not on a round area. But it is another thing to look at if you're really wanting to have the highest fidelity you can get. Another question is there other ways to visualize the data besides a mesh or a height map? And absolutely there is. You can take, if you want to ignore 3D altogether, you can take just a two-dimensional approach and solve your navigation problem using just an image. That would take a lot of programming and logic background to it. And I know there's a lot of also push to go the three-dimensional route to see what there is to see in these valleys and in these slopes from the first-person perspective. So with that, I think that's most of our basic questions we thought you guys might be interested to know about.
All right, we've got plenty of questions to take a look at and see if we can provide some responses. So this is for, I think most likely this is probably going to be for Tanner. Is Python the best coding language to use, and is Unreal Engine the most advanced game engine for graphics?
So yeah, I can definitely answer that. Addressing the graphics question. So there is, again, this is, kind of opinion based, but it is kind of widely agreed upon that Unreal is the definitely more capable in the graphics department. I think a large part of that is due to the Blueprint system, which allows you to create very complex shaders and materials much more easily with a much a less steep learning curve than having to learn how to write your own shaders in code, which is what you have to do in Unity. So as far as graphics go, I do think Unreal is the better choice there. And then as far as Python goes, generally Python and Blender work very well together, just because that's kind of the how Unreal uses C++. Python, or Blender, excuse me, uses Python as kind of its backend scripting. Now, and just generally, Python is a great language to learn early on. As far as syntax goes, it's very easy to pick up. There's a ton of resources about it, and overall, it's it's a powerful language with the learning curve that's a lot more tolerable than C++. So yeah, good question.
So Tanner, how can a team work collaboratively using Unreal Engine?
That is another great question. So there are tools out there to enable that collaborative, kind of remotely collaborative work. I am drawing a blank on the name, Jonathan, if you know it. It's kind of the GitHub equivalent that's used for Unreal. Totally drawing a blank on the name, but when we think about that, we'll put it in the chat. But yeah, so there are version control softwares out there, like GitHub is pretty widely used, that allows you to basically make changes and then push those changes that your teammates can then pull and work on the updated version. In the labs that I've worked in, we were less remote. And so what we did was we had several computers that were all on a local network. And so any changes that were made to the project were reflected on the computers in that room, essentially. So a couple ways to go about that. But yeah, I'd say GitHub is kind of the most widely used version control software for that.
Okay, great. So a couple questions about the ADC itself. Where's the data file you were talking about? That's located on the ADC website. You'll see a tile that says ADC guide and coding components available now. So that's where you will find that. There's a question about, let's see. Can both middle and high school students be in one team? No, those are separate. So you can only be on a middle school team or a high school team. Middle school is determined to be grades 5 through 8 for this school year, and high school is grades 9 through 12. And this is, I guess, a question for both of you. Which game engine do you recommend the most?
So I can take that one since Tanner's been talking. So it depends on what you're wanting to get out of it and the experience and expertise. From what I've seen from the different places I've been, is it's kind of a toss up on what you kind of rolled the dice to learn, and then they take that expertise to their next job and their next job, and that's what a lot of their foundation's built on. From the base level, Unity is widely known to be very easy to pick up and get started with and get things rolling very quickly. And as Tanner was mentioning, Unreal has some more powerful tools as far as out of the box, you're going to get a bit higher visual fidelity and a lot easier control over your graphics look. Whereas in Unity, you're going to have to learn how to write a few of your own shaders to tweak things or find libraries that do that for you. And so it's kind of an approach of which way do you want to go? Unreal has been publicly available since 2015. Unity has been publicly available since I think 2009 or so. So there are more resources out there for Unity, but I'd say both engines are fantastic routes to go.
Yeah, totally agree.
Okay, so some questions about how do you participate in the challenge, specifically about the teams. So this is a team-based challenge, and you must have a minimum of 5 students, and there is no maximum number of students on a team. Once again, in order to register for the ADC, you must have a lead teacher who will submit an email with an intent to participate and will include a signed letter of support from the principal or leadership of the organization that they represent. So I see quite a few of those questions. What do you do if you don't have a team? You definitely could start by working with a teacher at your school, and maybe that teacher can send out the information to the students about the challenge and see if anyone is interested. But I would definitely start with your school and a teacher or administrator that might be able to provide some support. Let's see what else we have as far as questions.
While you're finding that next question, I found the name of the version control software is Perforce, and I sent a link to that on our side of things. So if y'all could send that in the chat, that'd be great.
Okay, let's see if we can send that over. Okay, so for team members that are not familiar with coding, which language do you advise? You know, a lot about what we've talked about is kind of pointing you in the direction of Unity and Unreal for first-time coders. But any other thoughts on that, either one of y'all?
So from a game engine perspective, C# is definitely easier to get started with than C++, just because it handles a lot of things for you. You don't have to worry about near as much memory allocation or those kind of things. From outside of game engines, Python is probably the easiest, but neither of those use Python as their scripting language. So between Unity and Unreal, C# is probably easier to get started with than setting up the programming language. But like Tanner was saying, depending on how complicated you're going to get, that visual scripting component is also there for you in Unreal.
Okay, so we have a lot of questions and we are getting close to being out of time. If your question was not answered, you can go ahead and email us at jsc-m2mstem@mail.nasa.gov. I'm going to try to answer a couple of these relatively quickly. Some questions about using Scratch actually as your app development platform. I know there's a variety of videos online taking a CSV file and importing it into Scratch that you might want to check out, as well as utilizing the resources available to you. In the App Development Challenge Guide, it specifically talks about that each team must go out and find a community mentor to help them, participate in the challenge and provide guidance on how to create their apps. So you can definitely ask those questions of your community mentor. And then we also have NASA mentors available by request on a first-come, first-served basis. And we can match you with a mentor, and they can definitely help you with that. So if you haven't had an opportunity to do that, go ahead and send us an email requesting a mentor. And then let's see what else we've got in here that we can answer relatively quickly. Okay, so a lot of questions about Scratch came through. Do you believe someone with no coding experience can find a way to accomplish the requirements? Absolutely, and kudos to you for forming a team and actually participating in the challenge. Like I mentioned earlier, if you get some assistance from the NASA Community Mentor, they will definitely be able to provide some assistance on that. So I encourage you to stick with the challenge and seek out some assistance as best you can. So we are closing in here on the end of our time. And what I'd like to do now is just go ahead and share some information about some additional opportunities and what to do next. So In-Flight Education Downlinks is a 20-minute question and answer session where you as a student can actually talk to astronauts on the International Space Station. They are currently accepting proposals through their deadline of December 1st. So if you're interested in talking to an astronaut that's part of Expedition 65, which is in April of October of 2021, then definitely go ahead and reach out to this team. Check out their website for more information. The WARE Challenge is a challenge very similar to the App Development Challenge, and they are currently registering teams to actually create they're asking students to create a wearable radiation countermeasure for deep space exploration. So this is the Artemis program astronauts. You can actually help keep them safe by participating in the WARE Challenge. Check out their website as well as the information in the slide here for additional details. Once again, you want to register for that by December 1st, 2020. So what to do next? If you have not formed a team, we encourage you to go ahead and form a team and participate in the challenge. I do want to mention that one of the key things to register for the challenge is that your lead teacher must complete a Moon to Mars webinar, and those are actually located at the NASA STEM Educator Professional Development Collaborative. So we've put the link to the NASA EPDC there. We encourage you to go there, check out the upcoming events, and then attend the webinar. We will need your certificate of completion, so you just have to email that to us by the video submission deadline. Once again, that's November 18th at 2 p.m. Central Time. And when we last looked at the upcoming events, there were 2 Moon to Mars webinars tomorrow, October 15th, and then one on October 29th. But saying that, we'll go to the next slide. If you are a registered team and you are actively participating, we encourage you to share information with others. That's also part of your community engagement, which is in the ADC guide. So tell others about the program. We want to see as many teams involved as possible. Once again, the registration deadline is October 28th. And then we hope to see you at our next live virtual connection. This will be the last one that is available to everyone. And then the last virtual connection will only be available to registered teams. So like I said earlier, it's currently scheduled for October 28th. We're going to go ahead and change that to most likely the first week of November. But check in on the ADC website for the date and time change. And at this point in time, I want to just remind you that if you have any questions, go ahead and send those to jsc-m2mstem@mail.nasa.gov. And then if you also are working on the challenge and would like to share information in a different way, we encourage you to utilize social media, hashtag NASA_ADC or hashtag NextGenSTEM will allow us to see what you're doing and see how your team is progressing. So saying all that, I just want to take a moment to thank John and Tanner for their hard work to create these presentations. I know our teams will be able to utilize those moving forward, and we thank you very much for your time. Saying that, great job, teams. We know the teams are working hard to create their apps, so continue your work there. Once again, reach out to us with any questions, and we look forward to seeing you at the next live virtual connection. All right, teams, good luck.
Good luck.